The intermediate value theorem is an important theorem when it comes to graphing polynomial functions. It says, suppose f is a polynomial function and a comma b is an interval of which f of a does not equal f of b. If k is a number between f of a and f of b, then there is a number c in the interval between a and b such that f of c would equal k. In other words, a polynomial function takes on every value between any two of its values, and this helps us draw a smooth continuous curve when we actually graph a polynomial function. Now we're going to look at three types of symmetry, and some of these, we've already looked at all these types, but we're just remembering. A graph is symmetric about the y-axis if f is an even function and if f of negative x equals f of x for any value of x in the domain of the function. So it's symmetric about the y-axis. It's symmetric about the origin, and f is an odd function if f of negative x equals negative f of x for any value in the domain. And the graph of a quadratic function is symmetric about its axis of symmetry, which is x equals negative b over 2a. Discuss the symmetry here. Well, it is not a quadratic, so then let's find what f of negative x is. So that's 8 times negative x to the fourth minus 3 times negative x squared. Well, negative x to the fourth is just x squared, so I have 8x squared minus negative x squared is just x squared, so this is 8x to the fourth minus 3x squared. Oh, that's f of x. So f of negative x equals f of x. So this has symmetric to the y-axis. Here, f of negative x is 6 times negative x cubed minus 9 times negative x. Well, that would be negative 6x cubed plus 9x. Oh, those are just the opposites of here. So this is the opposite of f of x, and that means this is symmetric to the origin. And this is an x squared plus x plus, we don't have the c here, but that's okay. This is a quadratic. So my h equals negative b over 2a, so negative 5 over 6, and so this is symmetric to x equals negative 5, 6. It's symmetric to this line, which is defined by an equation. Now we want to look at behavior at the x-intercepts. We've been working on finding the x-intercepts, but now we need to look at behavior. So if a is a root with a multiplicity of k for a polynomial function, if k is odd, the graph will cross the x-axis at that point a. But if a is even, then the graph touches but does not cross. It's like a polynomial. If this is the axis, it comes down here and touches at a. If it's an odd, this is the point A, then it will cross some manner. And here's an example here. My x's, x here will be 1/3, and x here will be negative 2 with a multiplicity of 2 because of this 2. So here it is, it comes up and touches but does not cross, but at 1/3 it crosses. So we can see how that happens then. Here they ask us to find the x-intercepts and determine the behavior of the graph at each of these intercepts. Well, this is in factored form, and this first 2x factor will tell us that x equals 0, and it's only once, so it crosses. This will tell us that x equals 3, and it's only once, so the graph crosses. And this is x equals -2, again only once, so the graph crosses at all three of these. But here we have in factored form, we have x equals 0, and that has a multiplicity of 2, so it does not cross. This will tell me x equals 2, but no multiplicity, so it crosses there. And x plus 3 squared, that means x equals -3, will have a multiplicity of 2, and it does not cross. Now this one, they weren't so nice and factored for me. So let's see, 1 and 2, 1, 2, 3, and 6. I'm going to try a -2. I'm going to try negatives because we have some sign changes here. I'm just going to pick -2. 2, -4, 1, -2, so -3 multiplies together, I get a 6. This is 2x squared plus x minus 3. 2x and x, and the only way to get a 3 is a 1 and 3. If I go 3 and 1, 3x and 2x, positive 3x, -2x, give me a -3 and a positive 1. So x equals -3/2, and x equals 1. So my intercepts are 1, and it crosses because there's only one of those. -3/2, and it crosses because there's only one of those. And -2, there's only one of those, so that also crosses.